This is lecture 17 on the central limit theorem and the delta method. So we've been talking about convergence for a couple lectures now. And today we're going to kind of talk about the crowning achievement of convergence topics in statistics and I would say broadly in mathematics. And that is the central limit theorem, which is maybe one of the most important theorems in all of mathematics. And the central limit theorem is going to tell us something about sums of random variables, generally. In the last lecture, we had looked at, among other things, we had looked at the laws of large number, say LLNs, or laws of large numbers. And we had a couple of different forms. We had the weak form, which basically said that if I have some uncorrelated random variables, then x bar will converge probabilistically to the mean. Basically, it said that if we had some xn, they're uncorrelated, and they have a mean, a shared mean, mu, and a shared variance, x, let's say sigma squared, then x bar converges in probability to mu, the true mean. And that makes us happy because we use x bar to estimate the mean. And this tells us that, yes, for large samples, we don't need any real strong conditions. We need some uncorrelatedness. We need a finite variance. But if you have that, then if your sample is large enough, x bar is going to do a reasonable job at approximating the mean. We also had a stronger form of the law of large numbers. There, we not only needed uncorrelatedness, but we needed the xn's to be independent. So they're independent, they have a mean mu, they have a variance sigma squared. If that's true, then xn bar converges almost surely, in a stronger way, to the mean mu. So really, one way you can view the conversation of discussing the law of large numbers is as a conversation about sums of random variables. So what we've seen is that let's say first of all, if I take a sum of some random variables, maybe they're uncorrelated, maybe they're actually independent, we can make this converge to our mean, mu, of these things, under some conditions. If I normalize this sum by 1 over n, by 1 over how many of them I'm looking at, and we can think of this mean, mu, as some degenerate distribution. So yeah, it converges kind of to a single value under some conditions. So this is the strong law of large numbers, the weak law of large numbers. So these would be my laws of large numbers. We could alternatively ask a question: what if I just look at a sum and I don't normalize it? And generally speaking, this thing is going to blow up. So basically what I mean by saying it's going to go to infinity is it's going to blow up, or it's going to not converge. So if I normalize my sum by 1 over n, call it a mean, we get collapsing to a point value. If I don't normalize, I'm not actually going to get collapsing in any kind of probabilistic sense. And so the question is there something in between? Can I get something that doesn't blow up with, say, no normalization, but is there some form of normalization that will get it to collapse to a non-degenerate distribution? So if I look at a sum of random variables, is there some constant out front that I can put in front of them so that they, some quote, rate of convergence constant I can choose so that this thing converges to, in distribution, to some non-degenerate distribution. And that is basically what the central limit theorem is telling us. And indeed, the answer the central limit theorem says is that under certain conditions, if I put not 1 over n, but I put 1 over root n, so I do some kind of proper scaling, then I can get this to converge to a non-degenerate distribution. And that's really interesting. And that is basically the central limit theorem in a nutshell. So the central limit theorem is talking about, well, basically, how can I convergence of sums of random variables? And how can I normalize these conversions of sum of random variables in a way to get it converged to a non-degenerate distribution? So we can write out the statement of the central limit theorem. It's actually not that bad. This is, something that is used all the way down into intro stats, but we don't really, you don't see obviously the formal statement of the central limit theorem. But now that we've taken so much math and so much probability, it's actually not so bad of a statement to make. And that is kind of the power of it. It is a very general theorem. And I'm guessing the name central limit theorem comes from the fact that it is a centrally important limit theorem. The limit theorem, because it says something about limit of random variables, and it is centrally important. So the statement. The statement is that if, let's say I have some x sub n's that are IID with, of course, all their means being mu, and their variances being sigma squared, and that variance has to be finite, then typically the way it's written in an upper level stats course is, if I look at the quantity x bar, that will depend on kind of n samples, subtract off that mean, I divide through by my standard deviation, and I multiply on the outside of this by square root of n, which is basically my scaling factor. This quantity will converge in distribution to a standard normal distribution. So that's the whole statement of the central limit theorem. It's really not that bad of a statement. You have some xn's, they're IID, have some mean, have some finite variance. If I properly scale this thing, it converges to a standard normal. So the central limit theorem is why normal distributions, it's one of the reasons why normal distributions are so important. I mean, normal distributions have very deep connections to many places, but this is one of them, which is that, turns out, x bar, properly scaled, will converge to a standard normal. And so that normal distribution is really special in some ways. There are lots of other bell-shaped distributions out there. There are lots of other distributions where we have nice properties, but none of them as nice as the fact that it is kind of an attractor in the space of distributions. That is, if you properly normalize the sum of other random variables, everything converges to it. Some other comments are that, so we have this finite variance restriction, so that is necessary beyond the scope of this course, but you can relax these things and you can get other, if you, there are a set of distributions that are kind of attractors in the space of limits, and so but there aren't that many of them, and so there's kind of a family of things that properly normalized sums converge to, and normal distribution is kind of the most useful one because it's the one that corresponds to kind of our everyday life where we have finite variances. That is, things aren't too weird. So just a comment here, right? So if we go back up to, I talked about this kind of proper scaling here, notice that root n by x bar, let's say notice root n by x bar is square root n 1 over n, right, is basically 1 over square root n times the sum. So it's like root n times x bar, which is like a sum that's been scaled by 1 over root n. That's my connection to point 3 here, is that that's the crux of the theorem, is looking at sums of things that have been normalized by 1 over root n. There, it's a little bit of a cumbersome way that it's written. First of all, we have this root n out front, which is a bit weird. So there are a couple different kind of equivalent ways you will see it. The intuition, obviously, for the central limit theorem is that x bar is basically follows a normal distribution with a mean mu and a variance sigma squared over n, where n is your sample size. So this is like an introstats intuition, great intuition, and practically how people will use it, but not mathematically rigorous. And the reason is, so why can't I write this? The reason is basically, let me say, we rewrite CLT in a more friendly version like of this, say, like, can't I just move my n over? Can't I say something like x bar with n samples converges in distribution to a normal mu sigma squared over n? And the problem with this, and the reason you can't do that, is I have an n in my limit. And that is not allowed. Right? You can't have an n in the limit. You can't say that 1 over n converges to something involving n. You can't have an n in your limit, right? The point of the limit is it doesn't involve n. It's kind of a limiting behavior. So you can't, this doesn't properly make any sense to write in kind of a formal way. Nonetheless, the intuition is this first thing here, which is that, yeah, x bar is kind of approximately normal with the variance sigma squared over n. So the proper way to write it, and there's a couple different ways you'll see this. The first way is the way I wrote it up there, which is what you see in kind of more advanced stat textbooks. I'm not really sure why they like the root n up top, but you'll typically see this. All right, so that's the statement I had written. You can move the sigma squared over. That doesn't cause any issues because I can pull my sigma squared out of this thing. Sigma squared doesn't depend on n, so you could alternatively write it as root n by x bar minus mu converges in distribution to a normal 0 sigma squared, and that can be a useful way of thinking about it. Sigma squared is just a constant, so we can definitely just pull that over there. Unfortunately, I can't put my mu over there because that mu is multiplied by the root n, and I can't move that n over there. So either, I guess here, what's the third way? The third way was I can move my root n into the denominator, make it look more like a t statistic. This is less common, but it is nice because it reminds you of kind of a z statistic or a t statistic or something like that. So that's a fine way. That's also true, right? Algebraically, that's equivalent to way 1, right? Any of those are kind of proper ways of writing the CLT. Some other notation is that because people like this kind of first way here of saying, well, it's approximately this, you can kind of define a kind of approximately normal thing, kind of verbiage here. So what you could say is that x bar, some people write x bar is distributed asymptotically normal with a mean mu and a variance sigma squared over n. So this is called asymptotically normal. But this is purely notation for the CLT, right? If I write x bar is asymptotically normal with a mean mu and variance sigma squared over n, what I mean is that root n by x bar minus mu over sigma converges in distribution to a standard normal. So it's purely notational. Happy for you to use it. I will use it on occasion. That's a totally fine thing. Because at least when we say it's asymptotically normal, blah, 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 it's just rigorously defined as, this statement here. So you'll see that too. And I like that because it gives an intuition for what's going on. So let's look at a couple of examples, maybe. An example. Let's look at an example or two of the central limit theorem in action. So let's assume I have some data. Let's say maybe it comes from a Bernoulli distribution with a parameter p, right? And we can recall that here mu, which is just the expected value of any of these, is p, and our variance, which you might call sigma squared, which is the variance of any of these, is p by 1 minus p, right? So what's the application of the central limit theorem? CLT says something about square root n x bar minus mu over sigma squared, which in this case is root n. X bar is x bar, right? Now x bar we've actually shown is it's the UMVUE for p. It's also the MLE for p. And so we can talk about the asymptotic behavior of it. It is, CLT says that x bar minus the mean, p, over, whoops, that should not be a sigma squared, that should be a sigma. So what's sigma in this case? Root p by 1 minus p. That quantity will converge in distribution to a standard normal. So why might this look familiar? In intro stats, you might see something like, x bar as an estimate for, let's say, yes responses to a poll. So in an intro stats class, you would never see someone talking about Bernoulli distributions, but ultimately, if I do a yes/no poll, do you like 452? Do you not like 452? Right? All your answers are binary, yes/no. And so you could code them as zeros and ones, and you could think of this as the observations from Bernoulli. Maybe there's some true underlying proportion of students at the college that like 452, and I take a sample of one class, and I want to estimate that true underlying proportion. So I calculate the percentage of my class that says they like 452. In that calculation, if I encode yes as 1 and no as 0, that proportion is just x bar, right? X bar is the sum of the ones, the sum of the yeses, over n. How many are there, right? So that's kind of the sample proportion, you might call it. So often this will be called like p hat in intro stats. And in intro stats, what you would say is that p hat is kind of, approximately, for a large n, normally distributed with a mean p and a variance p by 1 minus p over n. And the way to say that in the proper 452 way might be to say it's asymptotically normal. That is, it converges in distribution to a standard normal in the right way. But you would use this and you'd say, p hat is kind of approximately normal with a mean p and a variance p by 1 minus p, and so maybe we form a confidence interval for p hat as something like p hat plus or minus, I don't know, some constant times root p by 1 minus p over n, but you replace those p's with p hats. And where do you get that from? Why are you allowed to do that in intro stats? Basically using the central limit theorem. It's basically this exact problem where you're saying, asymptotically it's normal. I'm going to estimate the variance by just plugging in the p hat into my my variance, and I actually know p, so you plug in p hat, and then you take plus or minus. It's normal distribution is symmetric, and so I can do if I want a 95% confidence interval, maybe I do plus or minus 2 standard deviations, and this is maybe my 95% confidence interval for p hat. And all of that is justified basically from the central limit theorem and this problem. So there you go. There's half of intro stats in one problem, right? We will talk in a couple lectures. We'll start getting into hypothesis testing and confidence intervals, and we will actually revisit this, hopefully, if we have time, and do that whole intro stats thing and prove that this is the best way to do it. Let's look at another example. I'm not going to be able to motivate this one as well, but you can take data. Maybe my data comes from a Poisson distribution. I like Poissons. The expected value of xn in a Poisson is lambda, which is also the same thing as the variance, right? The mean and the variance of Poissons are equal to lambda. And so what does the CLT say? Again, we saw that the MLE of this thing was x bar, right? That was true of the Bernoulli example too. And so actually what we're doing in this problem, this Bernoulli problem, is we're deriving the asymptotic behavior of the MLE. And you notice that the asymptotic variance here looks awfully familiar to the Fisher information. And so again, we have x bar. X bar was the MLE from this. X bar showed up all over the place as the U and BUEs, as the MLEs. And nicely enough, the central limit theorem says some nice stuff about the asymptotic behavior of them. And we'll talk next time about generally the asymptotic behavior of MLEs. But in this case, we don't need any more general theory. You asked me, what's the asymptotic behavior of the MLE for Poisson? Well, I can apply the CLT. The CLT says x bar minus the mean, which in this case is lambda, divided by the standard deviation, which is in this case, it's supposed to be a square root lambda. If I look at that and I multiply by root n, this thing will converge in distribution to a standard normal. So this is all setting us up for hypothesis testing or confidence intervals, because you can imagine the same way I was able to form basically an approximate or a large sample confidence interval for p hat in the intrastats example, you could do the same thing for a Poisson. I want a confidence interval for lambda hat for x bar. Well, I know something about if I properly scale this thing, I get some kind of asymptotic standard normal distribution, and we'll see that in a couple lectures down the road that for any MLE, you're going to be able to come up with a really simple confidence interval. And it may have something to do with the Fisher information, which is why I taught that to you. Okay. So that's kind of the central limit theorem in a nutshell for now. You want to do a proof of it? Well, you have no choice. So we can do a proof of the central limit theorem. I think this is kind of a really fun proof, because this is kind of this, the central limit theorem has this kind of lore associated with it. Everyone knows that x bar is kind of asymptotically normal. And you go through, most of your undergraduate career with this kind of lore sticking around in all these places. But the proof of this is actually not really that inaccessible at this point. And so we can look at a proof of the central limit theorem. If you thought that our abuse of Calc 2 was bad so far, we get to bring back some more fun characters from Calc 2. So I just want to remind you, and I talked about this last time, that if I look at the limit as n goes to infinity of 1 plus c over n, this has a limit of e to the c, right? So this is basically like a generalization of our limit definition of Euler's number, right? Okay, so stick that in the back of your mind for now. That will come at the very last line of the proof, or almost the very last line of the proof. And then I want to remind you of something you've probably willfully forgotten from Calc 2, and it's a theorem called Taylor's theorem. Named after a guy named Taylor, presumably. So Taylor's theorem says something about Taylor series, and it says something basically about polynomial approximations of smooth enough functions. So if I have a function, this is like the 2-minute review of Taylor series from Calc 2. I have a function g, and we're going to say it's a real valued function that is, let's say, some k times differentiable. The kth order Taylor polynomial about some point A, which is just some number, is, and we'll denote it T for Taylor, K for the order, and it's a polynomial, so it's a function of x, and it's a polynomial in a certain form. It is the sum, and let's say our index variable is r. R is going to go from 0 to k, and we look at the rth derivative of our function g, evaluated at our point A. So it not only has an order, it has a point about which the approximation, the polynomial is going to approximate g, divided by r factorial times x minus a to the rth power. So written out more explicitly, the zeroth derivative we're going to just call the function itself. So it's basically g0 of a over 0 factorial times x minus a to the 0 plus the first derivative of g at a divided by 1 factorial times x minus a to the first power plus g the second derivative at a divided by 2 factorial x minus a squared dot 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 and so forth. And so you can actually simplify some of these terms. X minus a to the 0 is 1, 0 factorial is 1. We're going to call the zeroth derivative is abusive notation, but that's just going to be our function g. And say the first derivative at a times x minus a, the second derivative at a over 2 times x minus a squared, etc. So typically we only need to really consider, and for this theorem, we're only going to need to consider 2 terms out, but up to whatever k terms. So this Taylor polynomial is basically a good approximation of our function. So if I have let's say I have some axes, and I have my point A here, and I have some function like that, and this is my function g, so this is there, and this g can be any kind of nice k times differentiable function. Turns out, I can basically, my Taylor polynomial might look something like that. Maybe that's my kth order. This is tk. And it's going to be approximate g, and it's going to approximate g well near a. And as I move away from a, this thing is going to not approximate it as well. It's not going to approximate g as well, but at least locally around a, the kth order Taylor polynomial is going to do a reasonable job approximating our function. And Taylor's theorem specifically tells us kind of exactly how well the approximation works. If we let r be our remainder, which is basically g minus t, then Taylor's theorem says that this remainder goes to 0 as x goes to a. That is, if I look at points near a, my remainders can go to 0, or my Taylor polynomial is going to approximate g quite well. And it's specifically, I'm not going to write all the details, but specifically, Taylor's theorem really tells us that it does this fast in some ways, and it tells us exactly how fast it goes to 0 as x goes to a. And the punchline of Taylor's theorem is that basically for x near a, we have g of x is kind of approximately tk of x, right? So t does a good job approximating g near a. Okay. So that is a review of Taylor's theorem and Taylor polynomials. And we're going to use that because basically the central limit theorem is combining all this convergence stuff we've done with Taylor series. So it's kind of a cute little combination of some math that we've seen. All right, so let me remind you of the statement. And then we can go through the proof. It's actually not too bad of a proof. The statement of the CLT says again that my xn's are IID, the expected value of my xn's is mu, the variance of my xn's is sigma squared, that's finite, and it then says that root n by x bar minus mu over sigma converges in distribution to a standard normal. Okay. So that's the statement of the central limit theorem. So, okay. Let us first define some yNs, which are going to be our basically standardized versions of our x's. So we're going to take our x's and we're going to subtract off the mean and divide through by sigma. If we do this, then the expected value of my yNs is 1 over sigma expected value of my xNs minus mu. That's by linearity of expectation, and that's 0, right? Because this thing, this expected value of xn, it's also mu. Okay, so I basically standardize my x's, and we can play a similar game with variances. The variance of this thing is 1 over sigma squared times the variance of my xn, which of course is sigma squared, and so we get 1. So I'm going to form these yNs, which are going to basically recenter it and scale my my x's. Get that out of the way, make things easy. These new y's have univariance and 0 mean. Okay. So if I do that, I'm going to call y my quantity of interest, right? So my quantity of interest that I want to study is this thing x bar minus mu over sigma, right? And I want to show that this thing distributionally converges to a standard normal. If I define my yNs this way, I can expand out what this thing is, right? This is 1 over n times the sum the xn, so that's x bar minus mu. We got a sigma in the basement. And we're just going to do some algebra. What can I pull out of this? I can definitely pull out my sigma. So I can pull out my 1 over sigma, right? Maybe I want to leave that 1 over sigma in there. Let's just push my root n through. Yeah, let's push that root n through. So if I push my root n through, there's a couple ways to do this one, but if I push my root n through, it's root n over n times the sum. And I'm going to, and I'll push my, something like that. No, let's just do this in a couple steps so we don't get too lost. So I'm pushing my root n through, so something like that. Whole thing over sigma. Is this the easiest way to do it? Yeah. So if I'm going to pull my sigma into my sum. That's allowable. It's just a constant. And so my sum is the exponents. I can pull that sigma in there. And then I can pull my mu in. But I'd have to divide through. I would have to divide through by n, right? This is what I want to do. Why am I pushing that root n around? Sure, let's do that. I can pull that in. So what I want is that this in here, right? And in order to pull that into my sum, so I have my root n, and I surely can divide through by n, right? Like that. let's back up here for a second. So just before this gets too many root n's running over the place, right? So if I bring this in here, I have to multiply. If I want to bring this term into the sum, I have to multiply by n, right? And so one easier way to do this maybe is just to say it's something like this, right? So let's not distribute through that root n. Okay, so let's just say y is this thing, right? Which we just expand out. And I can factor out this 1 over n. That's probably easier. And I get the sum of the xn's minus n mu. Now, sum of the xn's minus n mu, I can bring that mu into this thing. So that would be root n over n times the sum. Certainly I can bring my sigma in that sum. And I can bring my mu in too. Except I drop my n. So this should be xn minus mu over sigma. So something like that, and actually I don't need my outside paren. So you gotta believe the algebra of the step, right? I can bring that mu into the sum, and I drop my n. Alternatively, right, the alternative is that you know, the sum of xn's minus mu in the sum is the sum of the xn's minus n mu's outside the sum, right? So that's all I'm doing there. So that's what that step is. But what you can see when I do that is, first of all, I can simplify root n over n to 1 over root n. And I can simplify this sum as the sum of myyn's, right? So here, now we get 1 over root n times the sum of myyn's. So all I've done is basically convert it to a standardized scale. You could alternatively prove this thing and just assume, without loss of generality, that x's have a mean 0 and variance 1, but it's not too consequential. And so we have this 1 over root n times the sum of my standardized x's. We call them y's. And recall that my y's are independent. They're independent because the x's are independent, and then I just do a simple transformation of the x's to get the y's, and the y's are independent. And you get this normalized sum, which looks a lot like that normalized sum I had talked about at the beginning of the lecture. 1 over root n times the sum of some y's, right? And because they're independent, if I look at the moment generating function, the moment generating function of y at some value t, this is the moment generating function of 1 over root n times the sum of myyn's at t, right? That's what we've just shown. Capital Y is that normalized sum of theyn's. And if we let m with no subscript y just be the MGF of any of myyn's, they're all identically distributed, so they're all the same MGFs, then we have a theorem that says the MGF of a sum of things of independent things is basically just the MGF of those things to the nth power. And if I scale something, I bring that scaling into my moment generating function. So if you go back to our original proof, maybe in lecture like 2 or something of x bar, we talked about the MGF of x bar. It's a very, very similar proof. Now we're talking about MGF not of x bar, or not even of y bar in this case, but something similar to it. So the MGF of my y is 1 over, is basically the MGF of any of my yn's, evaluating instead at t over root n, and you raise that whole thing to the nth power. All right, and this basically came from 2 rules that gave us this. 2 rules about MGS from 451 was that the MGF of a sum of things, of independent things, was the MGF to the nth power, and the MGF of a scaling of a random variable is just I scale, MGF of A times X was I just scale in my argument the MGF of X. So those are the two rules that give us this whole thing. Okay. So now we're at the part where we want to bring in the Taylor approximation. So let's consider a Taylor approximation of this moment generating function. Consider a second order Taylor approximation, or Taylor polynomial of my of t at 0. So our Taylor approximation is, you know what, let's not look at my, let's just look at m. Just make your lives easier. My is just a function of m anyways. Second order Taylor approximation of m says that m of t should be equal to m of 0 right, if we go back up to our Taylor approximation, it's like the function at a times the first derivative x minus a, the second derivative over 2 times x minus a squared, right? So, okay. So what do we get here? Plus, what is this? The first derivative, m prime of 0, times t minus 0, plus the second derivative, m double prime of 0, over 2, times t minus 0 squared, plus some remainder term, right? So this would be our second order Taylor approximation of our moment generating function m, of any of our little y(n)s. Now we should recognize some of these terms here, right? So first of all, we should say that m0, right, is the expected value of e to the 0 times whatever, my yn. It's just the expected value of 1 is 1. So m0 is just a number of 1. And we have, you remember back to 451, a theorem about the derivatives of the moment generating function evaluated at 0. In fact, the first derivative value at 0 is the expected value of my yn times t minus 0 is just t. And we have the second derivative is the expected value of yn squared. And t minus 0 squared is just t squared. And we know, if we go back up to our little yns here, we showed that the first moment is 0, and the second moment, which is going to be the variance because the mean is 0. And this variance is 1, so we get this thing goes to 0, and this thing, which is just the variance, is going to be 1. And so what we get for a Taylor expansion is 1 plus, well, that 0 term drops out, plus t squared over 2 plus some remainder term. So this is the moment generating function of any of my individual y's. Hence, if I look at finally the moment generating function of y, right, and y is our quantity of interest, right? Y is, if we go back up here, y is exactly what we want to show the distributional limit of, root n x bar minus mu over sigma, right? And so we said that this thing will be m, the moment generating function of the y's, evaluated at t over root n to the nth power, which is 1 plus t squared over 2, which is t squared over 2n, right? Because I square things. Plus r of t over root n, whatever my remainder is, to the nth power. So that is the moment generating function of y, my quantity of interest. Notice as n, my sample size, goes to infinity, t over root n goes to 0, and so my remainder will go to 0, and we're just going to kind of vaguely say very fast. Taylor's theorem tells us that goes to 0 very fast. So this looks like, is going to look like, asymptotically, let's just say, tilde 1 plus t squared over 2n to the nth power, i.e., if we look at the limit as n goes to infinity of this thing, we're going to get what? This looks like, if I were to pull off t squared over 2 into some c, this looks like, what? It looks like 1 plus c over n to the n, and we know the limit of that will be e to the whatever c is, and so this will be e to the t squared over 2. And we can recognize this is the MGF of a standard normal random variable. And so what we have shown is that y, which is root n over x bar times x bar minus mu over sigma, has an MGF that converges as n gets really large to the MGF of a normal 0, 1. And so since the MGF converge, the MGF of y converges, so the MGF converges to the MGF of a standard normal, so will the CDF. And this is a theorem that's beyond the scope of the course, but we only really need it for this one theorem. If the MGFs converge, so will the CDFs. And so since what we've shown is that the MGF of this thing converges to the MGF of the standard normal. And so if you believe my little asterisk here is that, so this means that the CDF of y will converge to the CDF of a standard normal. That is, by definition, fact that y, which is root n x bar minus mu over sigma, will converge in distribution to a standard normal. So that's our proof of the central limit theorem. A little bit hand-wavy in places, but that's the general strokes of the theorem. Not something you need to recognize, but I think we know enough now we can basically paint the major outlines of the proof. And the major outlines are basically, you can view this. So we're in this whole rigmarole with y's. You could basically state the theorem in terms of x's, where without loss of generality, you could assume the x's have a mean 0 and a unit variance. But you can basically show that this x bar can be written as some normalized sum, so 1 over root n times normalized sum. And if you look at the normal sum of independent things. And so the central limit theorem, in its core here, is just talking about normalized sum of independent things. So that's why I started off this lecture by saying that. Because the real mechanism of the proof is that, you can show the MGF of this thing takes on this certain form because of independence. And if we do a Taylor approximation of it, we get something that converges. We can show that this thing will converge, at least the MGF will converge to the MGF of a standard normal. And you have to believe this theorem that if the MGFs converge, then the CDFs will converge. And because the CDFs converge to that is definitionally distributional convergence. So I think that's a nice little proof of the central limit theorem, and really nicely wraps up that whole kind of mystery there, and gives a little more concreteness to it. It's actually not so bad of a proof that the central limit theorem is not this scary thing beyond the reaches of our grasp here, and we can actually kind of understand more or less what's going on there, and kind of bring some closure all the way back to, say, an intro stats course. Okay, so let's look at some examples, and we'll start talking about what's called the delta method. And so again, here's an example. If I have some xn's that are IID with a mean mu, which is maybe 2, and a variance sigma squared is maybe 9, the CLT, I don't need to know anything else about this. The CLT says that if I look at x bar, subtract off the mean and divide through by standard deviation, and I multiply outside by root n, the CLT says I don't need to know anything else about this. This thing will, with a large enough n, converge distributionally to a standard normal. And a follow-up question is, what if I, which we do a lot in this course, is what if I don't care about x bar, but what if I care about a function of x bar? Maybe what if I care about, I don't know, log of x bar? Can I say anything about the distribution of a function of x bar? And this is what is known as the delta method. So the delta method is going to allow us to talk about functions of x bar, and basically allow us to use the CLT not only to say things about x bar, but any kind of nice enough, slightly nice enough functions of x bar. Okay, let's write down the theorem. It's actually a little more general than just the CLT. So we're going to have yn be a sequence of random variables where root n times yn minus some parameter theta, or some constant theta, whatever, converges distributionally to a normal 0 tau squared distribution. So here theta is some parameter, or theta is some function of a parameter, and tau squared is some constant. And so this may be a weird way of stating it. Practically, for example, if the yn is x bar and theta is mu and tau squared is sigma squared, then the CLT always gives us a situation where this works, which is that root n x bar minus mu converges distributionally to a normal 0 sigma squared, right? So the reason that the theorem's written is not written in terms of x bars is actually a little more general. It doesn't need to be x bar specifically. It just means to be anything that has some kind of central limit theorem like distributional convergence. But the classic example that we're really going to use in this course is CLT. Okay, so that's just kind of an aside here. But we have something that behaves a kind of central limit theorem like theorem. Then if G is differentiable and G prime of theta, whatever that theta is non-zero, we have square root n G of yn. So this original statement we had is about the distributional convergence of yn, and we can basically say something now about the distributional convergence of G of yn, which is that G of yn minus G of theta converges distributionally to a normal distribution with a mean 0, but instead of, before we had a variance tau squared, now the variance is g prime of theta squared times tau squared. The g prime theta squared might look familiar, coming from basically, at the end of the day, the Taylor theorem. And we saw that in similar kind of thing in Fisher information, and it's all basically coming from Taylor's theorem at the end of the day. So let's look at an example, right? So what's an example? I have something of this form, right? Of course, I have my central limit theorem. The CLT says that root n x bar minus mu converges in distribution to a normal 0 sigma squared distribution, okay? And let g of x be log of x. So the question is, what can I say about the asymptotic distribution of log of x? Well, the delta method says all I need to do is basically figure out what my derivative is. G prime of x is 1 over x. And as long as that's not 0, which it won't be for any real number, then the delta method, also known as, we could more properly call this, so this is properly called the first order delta method. The delta method says that if I want to say something about g of x bar, it's true that g of x bar minus g of mu, if I multiply by root n, this will converge in distribution to a normal 0. And then we got to multiply sigma squared by g prime of mu quantity squared. So in this case, this is root n, 1 over x bar, g is log, right? Log of x bar minus log of mu converges in distribution to a normal, and g prime is 1 over x, so g prime of mu squared, 1 over mu squared. Mean of that thing is 0, and we get sigma squared over mu squared. I.e., x bar itself has an asymptotically normal mu sigma squared over n distribution, and log of x bar has an asymptotically normal distribution with mean log of mu and variance sigma squared over n mu squared. So either of these are kind of fine ways of thinking about it. This is the more formal statement of the delta method, but this is the kind of practical way that people think about it. So we look at an example, a proof, not an example. We look at a proof first, and I won't harp on about this, but the proof is again uses Taylor approximations, and so the Taylor approximation of G, let's say around theta, said G of x is approximately G of theta plus G prime of x times x minus theta. And so G of x minus G of theta is kind of approximately G prime of x times x minus theta. Whoops, not x bar, x minus theta. And so if we have that root n, kind of generically we have some sequence of yn's where yn, root n, yn minus theta converges to a normal tau squared distribution, then if I look at g of yn minus g of theta, this should be kind of approximately g prime of should not g prime of, I don't know why I wrote x here, right? This is theta, right? Gotta get my Taylor approximation. This should be a theta in here. This should be approximately g prime of theta times my yns minus theta. And so if I multiply by root n out here, and then multiply by root n out here, this is g prime theta root n yn minus theta. And we know that the second part here, this thing, converges in distribution to a normal 0 tau squared. And so my whole thing should converge in distribution to a normal, but instead of a tau squared, it would be like some constant multiple of that. So if I multiply my normal distribution by g prime of theta, my variance will go up like g prime theta quantity squared. And so that's where we get this from. So it's actually a kind of really simple, I mean, that's a bit hand wavy, but that's a really kind of simple, again, use of Taylor's approximation. Maybe we'll do one more example. Let's say let xn be IID from some Poisson distribution. And then the CLT says that root n x bar minus lambda over root lambda, right? We did this before, converges in distribution to a standard normal. So that's the CLT. And consider maybe g of x is 1 over x. Why not? Okay, right? Maybe we want to know about how 1 over x converges. Then the delta method says that g prime of x is negative 1 over x squared. And so before we had x minus lambda, we can now look at 1 over x bar. Whoops, maybe we should write it this way. This CLT can be written as root n x bar minus lambda converges to a normal 0 lambda. Doesn't really matter, but this is typically how people write it for the delta method. 1 over x bar minus 1 over lambda. If I look at that, delta method says that this converges to a normal 0, and I have to multiply by now negative 1 over lambda quantity squared, g prime of lambda squared times lambda, and that is, of course, a 0, 1 over lambda distribution. So basically, i.e., that, well, x bar may asymptotically be normal with a mean lambda and a variance lambda over n. 1 over x bar is basically asymptotically normal with a mean 1 over lambda, so that's nice, and a variance that is 1 over lambda, 1 over n lambda in this case. So that's cute. Basically just allows us to flip our lambda upside down. We want to look at the asymptotic distribution of x bar. So while for a finite sample, you know, the distribution of 1 over x bar, if x bar is Poisson, may be really complicated, asymptotically you can kind of nicely just play around with the parameters. And this is where a lot of kind of this is asymptotically everything works out nicely. And this is why people are kind of interested in asymptotics, right? Asymptotically things are normal. And so that's why things like the central limit theorem or delta method make our lives easy, because a finite, deriving a theory for a finite sampling may be very, very, very complex. But asymptotically, things are actually pretty easy to work with, and I can just flip my lambdas upside down. If I want the distribution of 1 over x bar, let's flip my lambdas. It works out pretty nicely. Okay, so we're going to stop here because we're at time. Today we went over the central limit theorem and we started talking about the delta method. Next time we'll finish up talking about the delta method and talk a little bit about the asymptotics of maximum likelihood estimators.